So nobody wants to phone in here? I guess they left here late. It must have been left here late Friday. We would have been the last class in here on Friday. Okay, so I got a bunch of these from chapter 13, Equilibrium. Under the heading Test 2 stuff on D2L, there's a couple of things I want to add to this before I start putting chapter 14 on here. So I figured we can review this, and I hope we get through chapter 14 before we go on break. And then we won't have much to do after break. When do I have the test? Yeah, but it's not the week after break, right? It's the 27th. So there's break. Oh, it's that Friday. That'll probably be okay. If anything, I'll push it to this Monday. So no lab this week. Okay. So let's review stuff that I have up here. I haven't edited these, so we'll see how well I do. Did y'all look at these? Anybody start any of these? If that is a no. Hold on, let me add the enumeration here. So everything I put on here, I did algorithmically. Let's see if I failed it or not. So on the test, there's only going to be A, B, C, D, or E. For some reason, I went a little nuts when I made this. So what's the expression going to be for this first question? Or under state reaction quotient. Question 1. Is it A? So these have to be in the numerator, and that's in the denominator. So that should be the answer. How about this one? Any duplicates? B? Do all of you see why this is B? Huh?
Because they're solids.
Yeah, because of the solids. And since SO2 would have been on the top, and there's nothing on the bottom, it just reduces down to here. Okay, y'all are probably good on these. Y'all remember running into something like this last semester? It says CuSO4 dot 5H2O. Remember seeing that anywhere? Okay. It's just called a hydrate. So you consider this whole thing a molecule. It's just written this way because 5 water molecules are stuck to this. And then over here, the 5 molecules have split away. So this is all one molecule. That's what I explained over here in the parentheses. All right, so which one is that? What is it? Yeah, that's right. This one. Yes, that one is, what did you say? D as in dog. So that's a solid, that's a solid. There's a gas. So that goes on top. About this one. Yeah, that's D. You guys okay with these? Should I keep going? If you want to check the questions. This one. Did you say B? CO2, you leave out the H2O. Got a square on the other two. I don't have the enumeration for this one. This is the last one. H2 squared, H2 third. switching. All right, these you have to calculate. Any LTDs? All right. So what is the expression for that? Do you know what it would be? You want to try calculating it? First, write the expression. And then don't forget the square for this one, this, and the cube for this one. And then you just plug in these, and you're either going to be higher or lower than KC. For these in the hint, I put what I found for KC, and that'll help us figure it out if I get it wrong. But see if you get 25 for KC.
Not 25.
You did? You did?
Yes.
Yay.
What's that mean, though?
Huh?
Like, what does the 25 say as
Well, that means, here's KC. This was, I should have called that QC. Crap. Anyway. I fix that too. So QC is 25, and then it's going to go back down to 17. So if it's going down to 17, does that mean it's shifting right or left? Higher to lower means shifting left. Yes. You guys understand that? Shifting left. You guys get that? Did you get 25? I guess I'll explain. So this is question 1. The initial concentration predicts direction. And it is significant that these are all gases. So you should start with an expression. This will go on bottom, these go on top. So concentration of N2, concentration of H2 to the third power, and then on the bottom, concentration of NH3 squared. That gives you, it gives you Kc. C means we're doing this by concentration and not partial pressures. K means we're at equilibrium, what it equals at equilibrium. And we're told, what does it say, 17? Is that what it says? It says that it's equal, at equilibrium when Kc equals 17. The answer to this. We're actually calculating Qc because we're away from equilibrium. And then NH3 was 0.20, NH2, 1.00. I try to do a fancy one, it never looks quite right. H2 is 1.00. Stick to normal one. And if you crunch that out, you get 25. So we're at 25. If I make a number line and I say K is at 17, and we're up here at 25 at QC, that means it has to go down to get back to equilibrium. For the answer to this, to go from 25 down to 17, it has to get smaller, which means this has to get bigger and this has to get smaller. And this is this side, and this is this side. So if this is getting smaller, these are getting smaller while this is getting bigger, so it's shifting left. Okay, yeah, I'll leave it at that. Did you go through all of these? Those of you that looked at them, did you go through all? Okay, try this one. Question 4. I calculated, so there's QP. So this one's just done by partial pressures, but it's exactly the same. You guys want to try this one? See what you get. I had QP1. Yeah, if everything's 1, then even the squares don't matter. It's going to come out to 1. So this one should be easy just by looking here. If these are all 1, once you plug everything in, top is going to be 1, the bottom is going to be 1, and the whole thing is going to equal 1. So now we're going up. So an increase going from 1 up to 16.5 means we're going to the right. Correct?
Yes, sir.
But if you're not clear on these, practice them or ask. Everybody okay with these? You've got at least those two. All right. Converting between KC and KP. You try these. Okay. It is simple algebra. It gives you KC and it says find KP. The temperature is important because you need to convert that to K. So number 1 in KC, KP. I don't mind giving you this formula on the test. The formula is KP equals KC RT delta N. I'll give you R2. R in this case is R equals 0.08. 206. 206, I think that's right. 206. 08206. Okay, I'll give you that on the test too. That's R. What's our temperature here?
400.
Back to my pictures. But we need to turn that into K for this. That has to be in K. So add 273. 673K. And then N, remember what N is? Here's the reaction. N2 gas plus 3 equals 2. Equilibrium, 2 in each. 3. That's a gas, that's a gas. And this is a gas. So you have to ask yourself this, how many moles of gas are on this side?
4.
There's 4. That's a gas, so I've got 3 there. That's a gas, so I have the invisible one here. So I have 4 moles of gas on the left side. And how many moles of gas on this side? 2 moles of gas. You always go final minus initial for anything that's a delta. So you're going to go 2 minus 4 equals negative 2. So N equals negative 2. So we have K, we have a negative 2, and we're given KC. We're also told that KC equals 0.50. So KP equals 0.50 KC times 0.8206 for R times
673 to the negative 2, to the delta. This is delta. N is what we always use for moles. I don't know why it's not an M, but again, blame chemists of yore for all this. Let's calculate this first. 0.08206 times 673. Now I can do, I think I can do powers of 10. Power 10. Not but my calculator does this. Four significant figures, 3, so let's just keep that. So this means 1 over, I had to do this the way my calculator does. So this times this, 55.2 squared. Down here I get 3047. I suppose I really ought to just keep 3050. It'd be easier to just do this. Get it. Try these. 560. No, the answer's not there. Did I do this right? Somebody else try this and see what you get. Did you get exactly what I got? 15. See what you get.
What the equation is exactly as it is if you feed into the calculator, gives the second question.
That's what he said. What did I do
Yeah,
wrong?
that's what I want.
What did I do wrong? I've lost my ability to do math.
I just plugged in like the initial, like the.
You can plug in that whole thing in your calculator.
Yeah, I did plug in all of it.
Well, do it that way. Apparently my old school way is just failing over and over. Move on, every quit looking at it. 08206 times 673 equals this. Oh, I didn't divide 1 by this. That's what I didn't do. Want to do another one of these? Let's do a KP to KC. So using that same formula, we're just using it the other way around. What is delta moles of gas here? For this one. This is number 3. How many moles of gas are on the left? 0. I gave the explanation for the hydrate again, so that whole thing, including the 10H2O, is a solid. And there's another solid on the right, and the only thing we see for gases is 10H2O on the right. And that's final, so that minus 0 equals 10, so the delta N is 10. So calculate and see what you get. Don't forget to convert the 25 degrees, add 273, see if you get one of my answers. I'm afraid to try to do it again because I'm just going to mess it up. I need to start using a scientific calculator up here. I think it's the 10 to the 39, if I remember right. Should I make you all do it?
I don't get answers, I'm not plugged in now.
Anybody? This is one I got out of business, so they should have to answer it. The way I remember it, is it's the one that's negative 39. I'd still like somebody to verify. Doesn't help me practice if the answers are wrong. Where are we? Equilibrium. Exercises. C for 25. Yeah, 5.3 times 10 to the negative 39 is what they both have. And I did it in a spreadsheet, that's what I got. Are y'all able to come up with this answer though?
I don't get it,
Huh?
so I can't get it.
I'm confused with like the delta in, because on both sides is at 11, and like they, would it be 0 then?
This is a solid, and this is a solid. So you only have 10 moles of gas on the planet. So it ends up being 10 minus 0 equals 10.
Is it negative 10 or is it?
10. Did you use negative 10?
I did.
So remember, it's final minus initial, so it's products minus reactants for moles. The book says that, and my spreadsheet said that too, so I think it's right. But I want you to be able to practice those.
All right, yeah, I got my point here, but 10 was 10.
Okay. All right, I'll take that as a confirmation. So I'll definitely have one or two of those on the test. Got two of them. Okay. Tim, predict directions. All right, for question 1, for temp predict direction. So what are you looking at here to help you decide this?
Like the delta H is positive.
So when this is positive, you pretend heat is on the left side. And then if you increase the heat, that is, increase the temperature, which way does it shift? Shifts to the right. Which is towards reactants. I just did it as product and reactants here, so that should be towards the reactants. You guys remember how to do this? You have this, and you have delta H positive. So ignoring that for now, if I increase the concentration of A, which way does it go to get back to equilibrium? If I increase A, it's going to shift this way. If I increase B, it's gonna shift this way. So it shifts away. If I remove it, it shifts towards. So if I remove some A, it shifts this way. I remove some B, it shifts this way. It works the same way here. If I put some C in, it'll shift that way. If I take C out, it'll shift this way. That's for concentrations. When delta H is positive, you pretend heat is over here, and then increasing temperature shifts that way. Decreasing temperature shifts this way. It's the same idea. And if this is negative, then you pretend heat is over here and you just play the same game. Here, increasing temperature will shift it that way, and decreasing temperature will shift it this way.
So does that one shift towards the products if it's positive?
Oh, yeah. All right, this one. Positive.
Shifts towards products.
This one's negative.
Negative.
Negative. Notice this, these all say increased temperature. I should have thrown some decreased temperature in there so it would go the other way. But let's finish this the way it is. If I increase temperature here, which way does it shift?
Products.
Okay, look at this one. What if I decrease temperature, not increase? What's that mean?
Products.
Heat's on this side, decrease temperature, yeah, then it'll go towards the products. You guys okay with this? That one's going to be here. So it doesn't increase. How about this one? Increased temperature, what happens? This one, increased temperature, what happens?
Products.
All right, for these pressure ones, the delta H is a red herring. That doesn't have anything to do with the delta H. You remember what to do here?
It goes to the side of last one.
Yep. If you increase pressure, it tries to compress as small as it can be. On the right side, you have 4 moles of gas. On the left side, you have 2 moles of gas. So if you increase the pressure, it squeezes into a smaller space by shifting left. Remember that? Increase the pressure here, what happens?
No change.
No change. Same amount of gas on both sides, 2 moles on both sides, so now the pressure doesn't change anything. There's no better side to squeeze into, so it's just, there's no change. How about this one?
Yeah. You said delta H doesn't have to do with it.
Yeah, doesn't have anything to do with it. It says increased pressure, delta H here is a,
Shifts left.
you increase the pressure, it'll shift left towards reactants because that's a smaller amount of moles. You got 3 moles of gas on the right and 2 moles of gas on the left. So it'll shift left. And again, I had increase for all of these, I could do decrease. Like what if this said decrease, which way would it shift?
The bigger side.
If you decrease the pressure, then it can expand a little bit. So this one only has gas on the left and no gas on the right. So if you decrease pressure, it'll shift left a little bit. Because it can expand a little bit. That makes sense? Let's go through all of them. What did this one do? Increase the pressure. It it will shift with reactants. This one, increased pressure, no change. Here, increased pressure, it'll shift to reactants. Increased pressure here, what will it do? Increased pressure goes towards products here. I said to pretend what happens when if it decreases, but I'm going to answer this the way it's stated. If I increase here, it's going to go to the right because that's a smaller amount. So this one goes toward products. Do you see that? Increased pressure here.
Reactants.
3 moles of gas on the right, 2 on the left, so it would go towards the left. 4 moles on the left, 2 moles on the right, so increasing pressure. Products. How about this one? Yep. There's 2 moles of bromine gas over here, and 1 mole of bromine gas over here. So yeah, towards products. How about this one? This one, no change. Because there's 2 moles on the right and 2 moles on the left. Still looking for my answers. This one was fun to make in the spreadsheet. All right. Fractions at equilibrium. How would an increase in H2 affect the concentration of everything there? So once it goes back, it's sitting in equilibrium, you put some H2 in, you wait for it to go back to equilibrium. Now, did it increase or decrease from the way it started, H2? If you increase the amount of H2, once it gets back to equilibrium, there will still be a little bit more H2 than there was to begin with. All right. The other one should be obvious, though. If you increase the H2, equilibrium shifts to the right. So that means CO2 is going to go down and CH3OH is going to go up. So we're looking for increase, decrease, increase. Increase, decrease, increase, is that it? I had fun in the spreadsheet for this one. All right. Same equation, but now we're increasing the concentration of CO. So if you increase the amount of CO and then it goes back to equilibrium, what was the change for H2? So H2 should be decrease, CO should be increase. So we're looking for increase, decrease, and increase. This one's going to increase because it's shifting to the right. Increase, decrease, increase. So it should be that one. Increase, decrease, increase. Okay, we'll see. Same one, but now we're adding CH3OH. Yeah, increase, increase, increase. Across. You guys see this? If I increase CH3OH, some of it will go back to the left, but it'll still be left with a little bit more than it started, and then these will increase as well. I just realized I need to change these up and say decrease sometimes. What if this said decrease the amount of N2? Let's pretend that says decrease the amount of N2. So if it's sitting there at equilibrium and I remove some N2, where is N2 once it gets back to equilibrium? It's a decrease, is that what he said? It will decrease a little bit. What will happen to O2? It will increase, and NO will decrease. So we're looking for, except this says increase, so I need to go back and change these up a little bit. So this one should be increase, so this should be increase, decrease, increase. Should be this. Let's get those ones too. Let's see if my answer key is working. Increase H2, it's increase, decrease, increase. This one is good. Increase, decrease, increase. This is good. Increase, increase, increase. Increase it to increase, decrease. Increase. This increase, okay, like I said, I'm going to add a little more here for chapter 13, but let's do this. This one's asking what so this is now equilibrium concentrations. The first one I did where we were doing a calculation, they weren't at equilibrium. You just said, is it going to shift left or right to get back to equilibrium? This one is asking for the equilibrium constant, and it's giving you the equilibrium concentrations. So you just build that formula with this, and you just calculate and find out what KC should be. Want to try that one? I think that's the answer if I remember. Where you get 0.05999 2 3. Into what do you get?
106.
Did you get 5999?
Yeah, I did.
So my calculator when I did this, or the spreadsheet, 9998 something. So that rounds up to 0.0060. Sometimes I follow the significant figure rule. Sometimes I drop an extra one off just because I'm afraid that I'm not being careful enough with the spreadsheet. You know what one function of all the millions of functions there are in Excel that doesn't exist? Fucking significant figures. It will not do significant figures. I've looked online for formulas you can do, and there are these huge expanded formulas. I'm like, why is that not in an Excel? Yeah, I'm going to say fucking because it makes me mad. Well, it's so much easier. You want to do one more? It gives you the equilibrium concentrations. So you can just calculate it right. You want to try this one? Is that balanced? A. Yay. Only three of them? Let's say 1 out of 1 point. That's correct. That's correct. I don't know why it said 1 out of 1. So let me go over a couple more from this chapter that I want to put into D2L. Maybe just one more. I can't find any good ice table ones. It seems like this book, the only ice table one it did was that one example in the chapter. So I will look for some of those. Okay, this is similar. It's the same one we've been doing. Let me write it this way. All gases, which is important. All right, and they tell you 1.2 concentration, H2. And the question is, so these are all equilibrium. And of course, they give you what you need here is Kc equals. So find the concentration of NH3. Can you do that? It's that same formula, it's just the variable is somewhere else now. Square.
answer. Anybody trying to do this? Solve for x. This cubed times this, and then times this, and then square root. What'd you get?
I got that too.
Good. Did you get that?
Yeah.
Let's do one more of
Wait,
those.
so is that ice, like ice table?
No, no. It's just the same thing, and it's that same equation, and you just solve. Before I was saying solve for the equilibrium constant, and you had this. The ice table is when you're given some non-equilibrium concentrations and an equilibrium concentration of one of them. But I'll find some of those to do. Your book just only had that one example. And I went looking online to find some. I didn't find any good ones. But I'll find some that we can do. I'm pretty sure that's on the ACS one, so I want to do that. Let's do one more of these. What is this? I should say BRCL. And these are gases. And you're given, this one is, this. Partial pressure of CO2, 5 atmospheres, partial pressure of BR2.
If it's atmospheres, we just do the same thing.
Yeah, it's literally the same thing, but the formula you're going to write now is with P. I need to give you, so instead of Kc, I'm going to say Kp. It's 10 to the negative 2. And it's just Kp equals partial pressure of the products over partial pressure of Cl2 times partial pressure of Br2, and yeah, you square that, and that's what we're solving for again. So you're going to have an x squared again. The Kp is just for gases, and you can find that because you've got partial pressure of everything. So this one's going to be again, x squared, Cl2 is 115, Br2 was 450, Kp is 4.7 times 10 to the negative 2, and again, it's this times this, find the square root. Yeah. Yeah, 493. I looked that up in the book, and then suddenly they do two significant figures. Oh, it's because of that. I will do this multiple choice on the test. Okay. I'm encouraging you to look at these as they are, and make sure you're comfortable with it. I want to finish these and the acid-base stuff in D2L by the end of the week, so you have that to look at before break. You're going to forget it all over break, so when you get back after break, it'll be there for you to look at again, but I'm encouraging you to look at it before break, so you're not playing total catch-up. And as far as what else to do, acid-base, yeah, I'm probably going to do a little bit from chapter 15. It's more equilibrium, but now we call it the solubility product, but it's the same idea. It's for things that solubilize like this. And some acid-base stuff. Probably won't be the color thing. But I will probably do 15.1 and 15.2 before test 2. So it's chapter 13, chapter 14, and those first two sections of chapter 15. But I'll cover chapter 15 when we get back from break. I'm going to try to finish chapter 14 this week. No lab Wednesday, so I'll pick up again with the acid-base stuff, chapter 14. There's no lab this week. Some labs there's no week. Some weeks there's no lab. I don't think we'll get that far. I definitely am not going to do nuclear chemistry. Probably not going to do it again. But I might just pick and choose some bits from those, but mostly the lab bits. Test 4 will be the thermodynamics and electrochemistry. And that's probably enough for the test. I have to go look at the ACS file. I can go look at one and decide what's on there. If they got something, those other chapters, I'll try to get to it.